The term structure is applied to any arrangement of things that form a specific pattern. A bond is anything that holds two or more things together. Consider the reaction which takes place when sodium reacts with chlorine to form sodium chloride. Sodium atom reacts by losing its valency electron in order to acquire a stable noble gas electron arrangement. Chlorine atom reacts by gaining one electron on its outermost energy level in order to acquire a stable noble gas electron arrangement. In the reaction between sodium and chlorine, sodium atom loses its outermost electron to form a chloride ion. The sodium ion formed has 10 electrons and 11 protons, therefore it has net charge of 1 positive. Chlorine accepts a single electron donated by sodium into its outermost energy level. The resulting ion has 18 electrons and 17 protons, therefore the chloride ion formed has a net charge of 1 negative. The positive and negative ions formed attract each other, finally forming an ionic bond between them. Ionic bond is formed when an electron is transferred from a metal to a non-metal. Generally, reactions between metals and non-metal results into the formation of ionic compounds. Magnesium and oxygen combine ionically to form an ionic bond of magnesium oxide. Magnesium atom requires to lose 2 electrons to acquire a stable noble gas electron arrangement, while oxygen requires to gain electrons to acquire stable electron arrangement. 2 valency electrons are transferred from magnesium ion to oxygen atom, leading to formation of magnesium ion with a charge of positive 2, while oxygen atom gains the 2 electrons, forming oxygen ion with a net charge of negative 2. The 2 ions have opposite charges, therefore they attract each other, forming an ionic bond. Calcium reacts with chlorine to form ionic bonds of calcium chloride. Calcium loses 2 of its valency electrons in order to gain a stable arrangement. Chlorine requires to gain 1 electron in order to acquire stable electron arrangement. Therefore, calcium loses its 2 valency electrons to 2 chlorine atoms, leading to formation of calcium ion with a net charge of positive 2, while each of the 2 chlorine atoms gain an electron, acquiring a net charge of negative 1. The 2 chloride ions are attracted towards the calcium ion, forming bonds. Other examples of compounds that form ionic bonding include lithium fluoride and potassium chloride. The animation below shows the bonding in potassium chloride. Most ionic compounds form crystals. In the sodium chloride crystal, sodium ions attract the negatively charged chloride ions from all directions. Similarly, chloride ions attract the positively charged sodium ions from all directions. This type of attraction gives a 3-dimensional structure, where each sodium ion is surrounded by 6 chloride ions. Similarly, each chloride ion is surrounded by 6 sodium ions. Since there are very many ions in a unit, then the arrangement results in a giant ionic structure. Compounds formed through ionic bonding have giant ionic structure. Properties of ionic bonding. Solubility in water. Many ionic compounds dissolve in water. Ionic compounds have high melting and boiling points due to the strength of ionic bond. Electrical conductivity. Ionic compounds conduct electricity when in aqueous or when they are in molten form. In this lesson, we will discuss covalent bonding. Covalent bonding occurs mostly between nonmetal atoms. Hydrogen atom has one electron in its only energy level. This hydrogen atom combines with another hydrogen atom through sharing of their respective electrons to form hydrogen molecule. Click on the arrow to view the formation of this bond. Chlorine is in group 7 of the periodic table and therefore has 7 electrons in the outermost energy level. The electron arrangement 2, 8, 7 needs to gain 1 electron to get a complete outermost energy level or octet of 288. If it combines with another chlorine atom and shares an electron with it, a covalent bond is formed. Both chlorine atoms have an electron with it, then both chlorine atoms have complete outermost energy levels or an octet. The unit formed from the covalent bonding is called a molecule. The example of hydrogen, chlorine, and oxygen molecules shown represent covalent bonding of similar atoms. However, dissimilar atoms can also form covalent bonds. Hydrogen atom, for example, combines with chlorine atom to form a molecule of hydrogen chloride. Hydrogen and chlorine molecules are formed from covalent bonding. Similarly, 2 hydrogen atoms will combine with an oxygen atom to form a covalent bond of water molecule. In this case, hydrogen atoms and oxygen atom each contribute 1 electron for sharing. Eventually, hydrogen will have 2 electrons in its energy level similar to that of stable helium atom. Oxygen, on the other hand, shares 2 of its electrons with hydrogen for it to achieve a stable configuration similar to that of argon 288. Carbon atom combines with 2 oxygen atoms covalently to form carbon 4 oxide molecule. Hydrogen, oxygen, and nitrogen exist as simple molecular structures. The covalent bonds between 2 atoms, for instance, hydrogen atoms, are strong. However, the forces between the molecules are weak. The weak intermolecular forces are known as van der Waals. Simple molecular structures are gaseous in nature and have low boiling and melting point. They do not conduct electricity. The table below shows the properties of simple molecular structures. Giant atomic or covalent structures have a larger number of covalent bonds formed between atoms. The 2 examples of giant atomic structures are diamond and graphite. The following illustration shows a diamond structure. Each carbon atom in diamond structure is covalently bonded to 4 other carbon atoms. The basic unit is repeated in 3 dimensions to form a giant structure of millions of carbon atoms which are bonded to 4 other carbon atoms using covalent bonds. The melting point of diamond is very high. The reason is that diamond structure made of strong covalent bonds between the carbon atoms which require very high temperatures to break. Diamond does not conduct electricity because all its electrons are used for bonding. Each layer consists of carbon atoms covalently bonded together into hexagons. Adjacent layers are held together by weak van der Waals forces. These layers readily slide over one another, accounting for the greasy texture of graphite. Thus, 3 of its 4 outermost electrons are paired up to form covalent bonds. The 4th electron is delocalized, extending along the layers of carbon atoms. Graphite conducts electricity. This is due to the delocalized electrons extending along the layers and therefore free to move through the layers. Graphite has a higher melting and boiling point because it has strong covalent bonds between the carbon atoms, which requires temperatures to melt. Coordinate bond is a covalent bond in which the shared pair of electrons are donated by one atom. Consider a reaction which takes place when a hydrogen ion and an ammonia molecule combine to form ammonium ion. Hydrogen ion has no electron around its nucleus. On the other hand, the ammonia molecule has a shared pair of valency electrons that has not been used in bonding. The hydrogen ion combines with ammonia molecule. The hydrogen ion accepts the pair of electrons into its empty first energy level. The ammonia molecule donates the unshared pair of electrons. The animation below shows the bonding in carbon-2 oxide. An electrode in electrolysis. As a lubricant, this is because it is greasy and has a slippery feel. Diamond is used in making jewelry. Diamond is used in drilling rock. In metallic bonding, the metal atoms release their valence electrons and form positively charged ions. The electrons form a pool of negative charge around the ions. The electrostatic attraction between the sea of electrons and the ions is called metallic bonding. The electrons are said to be delocalized. Melting and boiling points of group 1 and 2 metals decrease down the groups due to decrease in strength of metallic bonds. All metals are good conductors of electricity because they contain delocalized electrons in their structure. In molecular compounds, the different molecules are held together by intermolecular forces called van der Waals forces. Van der Waals forces arise from the attraction between the nuclei of atoms in a molecule and electrons in the outermost energy level of atoms in neighboring molecules. Van der Waals forces arise from the attraction between the nuclei of atoms in a molecule and outer energy level electron of atoms in neighboring molecules. Van der Waals forces are weak. This accounts for the low melting points of many molecular compounds. In some molecular compounds, the molecule consists of 2 atoms, one of which has greater electronegativity than other atom. In the water molecule, oxygen has a stronger attraction for electrons than hydrogen atoms. The bonding electrons are therefore closer to the oxygen atom than the hydrogen atom. The water molecule is therefore polarized. The attraction between the positively charged hydrogen ends in some molecular compounds, the molecule consists of two atoms, one of which has greater electronegativity than other atom. In the water molecule, oxygen has a stronger attraction for electrons than hydrogen atoms. The bonding electrons are therefore closer to the oxygen atom than the hydrogen atom. The water molecule is therefore polarized. Ethanol molecules also form hydrogen bonds. The illustration below shows hydrogen bonds between ethanol molecules. The attraction between the positively charged hydrogen ends and the lone pair of electrons in the negatively charged oxygen end is called a hydrogen bond. The hydrogen bond is responsible for the relatively high melting and boiling points of water and ethanol. The bond is stronger than van der Waals forces but weaker than covalent bonds.